Hello everyone and welcome to the chapter 10 and 11 notes for the AP Chemistry chapters on solids, liquids, and solutions, or colligative properties as they're sometimes called. You should have already picked up the note packet from your substitute teacher. They're on the front lab table right over there, right there. Did you get them? Good, 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 good. You should see on the top of the packet the schedule for the next couple of days. Notice that we are expanded out from before break to after break. We have the dates for the lab, we have dates for tests, we have dates for some practice quizzes, we have when we're going to go over homework. This packet, I don't know if you noticed, but the packet is extra, extra thick. That's because I put in not just notes, a lot of homework practice, which we have scheduled to go over, several practice quizzes, which we're going to go over, some multiple choice, some free response. It's going to be fun. It's going to be great. So let's dive in to your first page of notes. All right, so on our first page of notes, we are starting to talk about inter and intramolecular forces. So these two types of forces, while related, drastically different. So let's diagnose or rip apart the prefixes. We have intra and inter. Intra essentially means within. Inter means between. So here we have two molecules. This is a molecule of hydrogen chloride, usually called hydrochloric acid, but since there's no water present, it can't be an acid right now. So we have hydrogen and chlorine. And over on the right, we have another hydrogen and chlorine. These are two separate, distinct molecules. What keeps a hydrogen bound to a chlorine is something called a covalent bond. Covalent bond is a force that's holding them together. That is an intramolecular force, INTRA. Intramolecular force. It is a covalent bond, and they are incredibly strong, incredibly strong. Now, if we have several hydrogen chlorides floating around, they might be attached to each other. The hydrogen and the chlorine from one molecule and the hydrogen and the chlorine from the other molecule are attracted to each other. And when they get attracted to each other, those two molecules form an intermolecular bond. The intermolecular bond is between the chlorine on the one molecule and the hydrogen on the other molecule. This bond is drastically weaker than the other bond. The bond inside the molecule that holds the hydrogen to the chlorine, or this hydrogen to this chlorine, is very strong, where electrons are actually being shared between the two atoms. Whereas the bond between the two molecules is not nearly as strong. So this is going to create some interesting dynamics as we move forward. You need to still be able to draw molecules. You need to be able to think about how they're built, and we're going to talk about polarity again. So here they are again, and below we have a bunch of tiny, adorable little water molecules. See, when molecules are polar, like hydrogen chloride or like water, dihydrogen monoxide, they are attracted to the other molecules that are also polar. Sometimes the attraction is strong and we have a liquid or a solid, and sometimes that attraction's really weak and we have a gas or maybe a liquid that just turns into a gas very easily. All of these molecules can be broken apart, but when we add energy, kinetic energy, and the temperature rises, though, it's key to remember that between this bond that's between molecules and the bond that's within the molecules, one is very strong and one is very weak. So as we heat a molecule up slowly, the molecules will break apart, but they're not going to break these bonds, the intermolecular bonds, the covalent bonds. They're only going to break these bonds between the molecules. So a lot of times we will be drawing a water molecule, H2O, and we'll be talking about it. But really what we need to visualize is something more like this. H2O is actually a giant field of water molecules, and they're attached to each other multiple times. And when we talk about boiling or condensing or vaporizing or sublimation or anything like that, we're really talking about the bonds between the molecules. We're not talking about the covalent bonds. That's a huge focus in this chapter is breaking those intermolecular bonds. I often use the abbreviation IMB for intermolecular bond. Didn't quite underline the M there. IMB, intermolecular bond. Just because intermolecular bond is quite a mouthful to say and or read. So the next strongest force by far is the dipole-dipole. Oh, wait a minute. My buddy Argon's still in the background. Just a second. There we go. If we're going to talk about dipole-dipole forces, you need to have a dipole up on the board. So what I have behind me is sulfur dichloride. That's sulfur to 2 chlorines. And since sulfur and dichloride is bent, there's these unshared pair of electrons on the sulfur. And with those unshared pair of electrons, there's always going to be a negative side to this molecule and a positive side to this molecule. So since it always has a positive side and a negative side, it's definitely going to have a dipole moment. Now, if we look at this drawing we have here, though, the idea is that each dipole has its own positive and negative value. And if you put a bunch of these sulfur and chlorines together, one SCl2 would be attracted to the next one, which would be attracted to the next one. And they would have a bunch of little magnetic fields that would then attract to each other. These forces between molecules, called intermolecular forces, in this case would be the dipole-dipole force. It's a pretty strong force. A lot of the molecules that you see that are liquids out there have dipole-dipole forces. Now the dipole-dipole force, though, is not the strongest of the 3 forces between molecules. Does anyone know the forces, the strongest of the 3 forces? Let us think. That's right. I heard you over there. We need to talk about hydrogen bonding. All right. This isn't going to be the last time you see me, but I'm here again. So hydrogen bonding is one of the 3 forces. It's actually the strongest of the 3 molecular forces. Keon molecule again. We're only right now discussing the 3, where's the camera? There it is. The 3 forces between molecules. Hey, what's a molecule? Molecules have 2 nonmetals. They're sharing covalent electrons, forming covalent bonds. And in this case, we're talking about some molecules that are then attracted to each other with particularly strong bonds. Why would these bonds be so strong, these hydrogen bonds? Again, my air quotes aren't both on there. Hydrogen bonds. Hydrogen bonds are strong bonds because hydrogen is such a weird element. Think about it. A hydrogen atom, right? There's a hydrogen atom, has 1 proton and 1 electron. That 1 electron is trapped inside the bond. So there's the electron. What is this hydrogen actually then? This hydrogen right here is not an atom. This hydrogen is a proton. And that's pretty weird. In all of the other cases, with all of the other bonds, with that dipole-dipole thing we saw ago, the chlorine had electrons around it. This is just a proton hanging out of here. That makes it super weird. For all of the other elements, it would be a completely different scenario, except for hydrogen. Now, hydrogen bonding, like we said, is a pretty strong bond, but it only really gets into consideration if the hydrogen is attached to a really strong, meaning electronegative, very electronegative atom. And the 3 strongest electronegative atoms are, all right, let's see if you can list them. The strongest electronegative atom is, I'm listening, you're right, fluorine. I heard you over there. Good job, Nick. Okay, the next strongest is oxygen. Yeah, good job. Good job, Joe. And then the third strongest, Emma? Yes, nitrogen. Good job, nitrogen. Of course, you could have probably looked right here, literally on the screen right now. Um, so I usually stop for a second and make some funny jokes about the fact that these three elements spell FON, and that's pretty funny. Or for those of you who don't like those types of jokes, who've had in off and off of those jokes, I'll stop. But hydrogen bonding can occur, A, with tiny molecules like water, because water has hydrogen, oxygen, hydrogen. Ammonia, that's what this is right here. This is ammonia, NH3. Or it could also occur in larger organic molecules. Here we have methanol. Methanol is a carbon, 3 hydrogens, and oxygen, and then a hydrogen coming off of that. But what's key with a methanol, and I hope you could see this, it's kind of hard to see even on the little screen I'm looking at, is that these 3 hydrogens that are on the carbon, they can't do hydrogen bonding. Why can't the 3 that are on carbon do hydrogen bonding? Well, there's a simple reason. Number one, it has to be nitrogen, oxygen, or fluorine on the hydrogen. Or you could go for the more advanced reason and say carbon is not electronegative enough to pull this electron bond over and really throw off the connection between the hydrogen and the oxygen. Whereas oxygen over here is plenty strong to pull the electrons from the hydrogen over that way and pretty much just leave the hydrogen as a proton. So now that this hydrogen is in a weird bond with this oxygen, this hydrogen is pretty much just a proton, and it can do hydrogen bonding with another element's electrons. That other element, though, still has to be nitrogen, oxygen, or guess what? That's right, fluorine. Good job. So here I have a nitrogen below the hydrogen, and so between the two of them, we could have hydrogen bonding right there. Yeah, that's what we're talking about. Hydrogen bonding. Drastically, drastically stronger than some of the other types of bonding. So again, we've already talked about that London dispersion force thing a second ago, but let's think about another, the element neon. Neon has a molar mass on the periodic table of 20.18 or something like that. I'm not sure. I don't have a periodic table, just pulling it out of my head. Neon has a molar mass of 20. What's the molar mass of H2O? Molar mass of H2O is oxygen plus 2 hydrogens, 18. So if water is 18 and neon is 20, they both have the same mass. Shouldn't they be just as easy to turn into a gas and make them fly away? No, they're not the same in terms of boiling point. That's what I mean by turn into a gas and make them fly away. It's a simple way. Boiling point is breaking bonds and making them fly away. The bond strength between the different molecules is very important. The mass is very important, and the bond strength is very important. So even though they have the same mass, because the hydrogen bond is so strong, it takes a lot more energy to excite those molecules, those water molecules, and make them fly. Now, water molecules are very strong. I've got a drawing over here on the left, and I mentioned that water molecules can bond in 4 directions, where NH3, ammonia molecules, can only bond in 2 directions. I'm really going to have to go over this in person with models in front of me to make it clearer, but really, if you think about it, each hydrogen can reach out to an electron pair on another oxygen. So one hydrogen can reach out, another hydrogen can reach out. But then on the oxygen, there's also 2 electron pairs that can have one hydrogen attach and another hydrogen attach. And with those 2 hydrogens attached, there's 2 connections on the oxygen. And then the 2 hydrogens are going to 2 other oxygens. So it's 2 out and 2 in. With the ammonia, there's only 1 pair of electrons per ammonia. So even though there might be 3 hydrogens reaching out, there's really only 1 that they can attach to ratio-wise. So there's going to be 1 that can reach out and grab on. The other 2 can't do anything. And then there's going to be a pair of electrons on the back of the nitrogen that can grab a hydrogen from some other NH3. So there's one out and one in. So that's why ammonia is easier to boil or vaporize than water. All right, let's see what else we can do here. So I think this might be slightly out of order. I talked about dipole-dipole, then hydrogen bonding. Usually, though, I talk about London dispersion forces first, because London dispersion forces are the weakest of the forces. And they're pretty interesting. But London dispersion forces also always occur if you've got any molecule at all, whether it's water or carbon dioxide or fluorine to fluorine, you have London dispersion forces. But where we first kind of like proved that London prove is strong, showed that London dispersion forces existed was with our noble gas friends. So noble gases are supposed to have this perfect distribution, air quotes, perfect distribution of electrons, but sometimes those electrons get thrown off. So those of you who like to draw a perfect Lewis-Dot structure are probably looking at this argon behind me, and sorry about this glare here, but the Murphy Chemistry home studio is not exactly up to par here for this job. So these electrons are not perfectly distributed. Most of you would probably really like it if I took this electron and moved it over there, right? Maybe moved it down here so it was more balanced. But I'm not going to. I'm going to irritate you for a little bit. Because when we're talking about London dispersion forces, we are talking about temporary dipoles. We are saying that these electrons are distributed wrong temporarily. And while they're improperly distributed, this atom has a very, very tiny, like a decimal of a fraction of a decimal charge on one side and a different charge on the other side. And during that momentary temporary dipole, it then has attraction between different molecules. Sometimes these instantaneous dipoles are set up by creating a big charge on one side. Maybe you throw a very hungry fluorine +2 over here. If you throw a fluorine +2 on one side, knock a bunch of electrons off the fluorine, it's really going to try to attack that noble gas. But we can also just do this with pure argon. If you cool argon off enough, it will turn into a liquid. It just has to get down to like negative, I don't know, 180. That's it. 190, something like that. Pretty cold is what I'm saying. Why does it have to be so cold for it to turn into a liquid? Because usually the electrons are moving and balancing each other back out at super cold temperatures. Those weak temporary forces can actually start to connect some of these atoms together and link them up in patterns over and over and over again. So the London dispersion force could also occur with any element or any molecule or anything, because all we're really saying is the electrons are off balance. Now, would you really care if a water molecule had London dispersion forces? What type of bonding is the strongest in a water molecule? Hydrogen bonding. Since the hydrogen bonding is so strong, that's probably what you're going to worry about. Yes, some of the electrons could be a little bit off balance and also add a teensy bit, but that's not really what you're caring about. Like if you were using a hammer to hammer in a nail, right? Hammer, 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 and then an ant crawled on top of the hammer also. It's not like the ant's going to add enough mass to really change what you're doing. So the London dispersion force is so weak, it's not really worth adding on to something like hydrogen bonding. However, if all you've got is London dispersion forcing, and you have a whole lot of it, say you got a giant pile of London dispersion forces, then it might actually add together to be something significant. Going back to my ant analogy a second ago. So sometimes with carbon chains, we might have a carbon to carbon to carbon to carbon, like a very long chain of carbons and hydrogens in a long pattern, like our gasoline, octane, and things like that. And all those carbons and hydrogens have so many little weak dipoles that they actually get attracted to each other and turn into liquids. But that only usually occurs with big, giant, long molecules where we get these London dispersion forces that cause liquids we observe. So in this first question, we're talking about the London dispersion forces that noble gases have. If you compare the noble gases, you'll first notice that the heavier the noble gas is, the easier it is to boil. One piece of advice I give everyone is convert these Celsius values into Kelvin. That way you can easily see which one is the lowest value, which one's the highest value. The lower a boiling point is, the harder it is to get it to liquefy, or reverse that, the easier it is to turn it into a gas. The higher a boiling point, the harder it is to get it to boil, the easier it is to liquefy. So we're comparing noble gas to noble gas to noble gas. Xenon has one of the highest boiling points. Radon would be higher if it weren't radioactive. We don't get to play with radon. But xenon has one of the highest boiling points for two very distinct reasons. Number one, it's the most massive of the noble gases. Again, setting radon aside, xenon's got the highest mass, which means it's going to be the hardest to accelerate and move into the gas phase. And number two, the other reason, is that its electrons are very far away from the nucleus. I believe xenon is 5s2, 5p6. Again, don't have a periodic table. And if it's 5s2, 5p6, its electrons are very shielded and easier to cause instantaneous dipoles. Yeah, instantaneous dipoles occur more often with more shielding. Let's look at number two. Put the following substances in order from lowest to highest boiling point. The one with hydrogen bonding would have the highest boiling point. Hydrogen bonds are very strong bonds and therefore hardest to break apart. So if you had a bunch of NH3s, they would be harder to break apart than the other two. And then the other two molecules, both are non-polar molecules. C2H6 is more massive, and it's going to have more London dispersion forces. It's a larger molecule, so it's going to be right there in the middle. And then fluorine to fluorine is the smallest molecule. It's the lightest of the three. It's also the most non-polar. If it's the most non-polar, it's most likely going to have the lowest boiling point. Again, really think about boiling point as breaking the molecules apart. The weaker bonds are easier to break apart, so weaker bonds have lower boiling points. Stronger bonds are harder to break apart, so they're going to have higher boiling points. Water has one of the highest boiling points of molecules out there, and it has very strong intermolecular bonds. Here we have just a simple flow chart to help you make some decisions. The left side of this flow chart is really all about what we were just talking about. If it's a polar molecule versus a non-polar molecule. We didn't talk about ions at all because ions aren't molecules, but we're going to talk about ions in just a minute, so hold off on that. So we're going to talk about liquids for a couple minutes. Liquids are caused within molecules. Liquids are caused between these intermolecular forces, whether they're the weakest, just London dispersion forces, all the way up to the stronger hydrogen bonding. When molecules are attracted to molecules, a lot of people call those molecule-to-molecule forces cohesive forces, if it's the same molecule again and again and again. If, however, that molecule is attracted to something else, like the glass in a beaker, or the floor, or a table, or your hand, then that molecule being attracted to you is an adhesive force. I usually think of adhesives like glue and tape to try to remember that it's between one substance and another substance. It's not within the substance. All of these forces are caused by intermolecular bonding, or the three basic intermolecular bonding we've been talking about. We have a picture of intermolecular forces here. So a molecule like water might have bonding in 4 directions down inside the water. But with surface tension, which is something you commonly talk about in some of your other classes, surface tension is a bit stronger because at the surface like we have here, you can't have any force going up because there's no molecules, no cohesive forces going up because there's no molecules above the molecules at the top. So instead, those 4 directions end up kind of flattening out, and the surface has an extra strong cohesive force. Over on the right, we have a picture of water molecule versus this is water and this is mercury. And I don't know if you can tell, but the water has that standard meniscus curve. Glass is made of silicon dioxide or some mixture of silicone with oxygen. Sometimes there's 1 or 2 other elements in there. But the hydrogen in the water and the oxygen in the glass are attracted to each other, and the hydrogen grabs onto it and creates this kind of meniscus because it's adhering to the glass. On the right side, though, we see that mercury behaves pretty oddly in glass. It actually forms a reverse meniscus. It's repelled by it. Actually, it's really attracted to itself. We don't deal with viscosity much. That question's in here, but let's just take 2 seconds. Viscosity is how quickly or how slowly a liquid flows. If a substance is really attracted to itself, it flows very slowly. If it's not very attracted to itself, it flows very quickly. Viscosity can be changed by the temperature very easily. People tend to think about water flowing, but a better example might be like honey or oil. Honey flows pretty slowly. Most syrups flow pretty slowly. How could you make, and if they flow slowly, then they must be really attracted to themselves. Yeah, they're really attracted to themselves. That honey's flowing pretty slowly downhill or down whatever it's going down. I know, anyway. How do you make the honey flow faster? Yeah, how do you make your honey or syrup flow faster? What's that? Yeah, just warm it up. All you have to do is warm it up. If you warm it up, the bonds are moving faster, and some of those intermolecular bonds will break and form at a faster rate. And if they're breaking and forming at a faster rate, then the molecules can slide past each other and roll downhill. So I'm gonna be honest though, it's probably not a good idea to microwave your honey. Sometimes when you microwave honey, you break some of the wrong bonds you don't want to break. It's always best to slowly warm your honey in warm water. We have a question at the bottom there. Oh, wait, question 6. Why do models of liquids tend to be more complex than either solids or gases? So with solids and gases, we have one extreme or the other extreme. With solids, the pieces aren't moving at all, so it's really easy to make a model of nothing's moving. And with gases, they're all broken apart and nothing's connected anymore. And that also is pretty easy because they're not connected anymore. But with liquids, the molecules are connected and breaking, connected and breaking, connected and breaking. And since they're going back and forth constantly, that's pretty hard to model. All right. And then there's a question there, number 1 at the bottom after 6, which doesn't make any sense, but let's pretend it makes perfect sense. Which would have a higher surface tension, H2O or C6H14? Take a second, draw H2O. Good. C6H14, it would be 6 carbons in a line, 1, 2, 3, 4, 5, 6 carbons, one connected to the other. And then the hydrogens would be a circle around them. There'd be 2 hydrogens per carbon, and then on the end there'd be an extra 2 hydrogens. So that's CH2, 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 CH2. And then the last and the first CH2 are actually CH3s for a total of 16. Well, because that C6H14 is all simple hydrogen to carbon bonds, it would all be nonpolar. That's going to be pretty easy to break apart. You don't have hydrogen bonding in C6H14. That's not fun enough for hydrogen bonding. You don't have a dipole-dipole in C6H14 because it's all carbon and hydrogen, very well balanced. You have London dispersion forces, pretty weak London dispersion forces. Now, you do have a lot of London dispersion forces because there's 6 carbons and 14 hydrogens, so it's highly likely that those electrons are going to be off balance in a bunch of spots. But nothing compared to that water molecule. Water molecules have hydrogen bonding. They're very difficult to break apart. We didn't spend a lot of time on liquids because they're so hard to model. We're going to talk about solids for quite a while. Solids fall into 2 categories, the amorphous and the crystalline. To be honest, we're not going to talk about amorphous much at all because they're disorderly and unorganized. We don't really have much to say about them. In crystalline, we have way too much to say about them. So amorphous solids are usually formed because you've cooled off something too quickly. Crystalline solids are formed when something is allowed to slowly cool off, and then you can get a pattern. If you have salt and you heat up sodium chloride to a couple hundred or thousand, I don't remember its melting point, until it's a liquid, and then you let it slowly cool back down. When it cools back down, you will get a positive one, negative one, positive one lineup in a perfect pattern. You'll get a crystalline solid, a regularly atomic arrangement with a perfect pattern. If, however, you flash freeze it with dry ice, you're not going to get a perfect solid. You'll get a random arrangement of sodium and chlorine. It won't be a nice crystal. It'll be horrible. You can also make crystals in solution. You can dissolve a large amount of salt in solution and then slowly let the water evaporate out, and then you'll get these like little crystal spears. Your textbook spends a lot of time talking about different crystal arrangements. We're not going into that. You can kind of just focus on what the heck is a crystal lattice and what is a unit cell. A lattice is this pattern arrangement, and the unit cell is the smallest version of that pattern. Look at that body-centric cubic one right there. That's the smallest version of a particular pattern. That pattern might occur billions of times, though, inside a crystal. That billions of times is the lattice. It's all of it put together, and the unit cell is just one of the tiniest pieces. We know these crystals exist because we have something, a tool in our toolbox called Xray crystallography. Xray crystallography is pretty cool. It's where you shine X-rays through something that's a solid, and then you watch the pattern on the other side. My standard example for this is I turn off the lights in the classroom. Okay, I'm imagining the lights are turned off right now. I then take a really powerful flashlight, I shine it at the class, but I pretend I can only see the shadows. If I can only see the shadows on the wall, can I figure out where everyone is sitting in the classroom? Probably not. Some of the shadows would line up with some of the other shadows and you would be missing. But I could start to infer something. And then I could go to a different place, turn on the flashlight again, and get a different image. Now, are you all in a regular organized pattern? Probably not a perfectly organized pattern, but there would be some arrangement and I maybe could infer it. Let's be honest, I couldn't infer it. But someone who is really good at this, like, I don't know, Rosalind Franklin or something like that, might be able to look at one of these X-ray images and infer from that image what the pattern was, or if there was a pattern at all. And then maybe you'd get credit for something important. And then someone else, well, or at least you should before someone steals your good work. If you don't know what I'm talking about, ask your peers. We're switching to one of our first types of solids. We're going to talk about metallic bonding for a second. Metallic bonding deals with metal-on-metal attraction. Metal-on-metal attraction often has, and I don't see it in the notes here. Okay, it's not here. That's irritating me. I thought it was supposed to be here. Okay, take 2 seconds and write out C of delocalized electrons. And I see the word delocalized here, but I don't see the rest. C of delocalized electrons. That's SEA, delocalized electrons. So when we talk about metallic-metallic bonding, we have all these metals like copper and gold and platinum or I don't know, lithium, and they don't have very strong electronegativities, and they have a lot of electrons on their valence shell that they're not sure what to do with. And so those electrons often shift between one metal and the next metal, and they say they're delocalized. They're not stuck on one atom. They move from one atom to another atom to another atom. They're delocalized. Yeah, okay. Now, what we can also say, though, is because they're delocalized and they're easy to move, this explains the fact that we know that metals are good at conducting electricity. They can shift electrons along pretty easily. So if you flip on the light switch, the electricity flows into the first element, which then bumps its electrons onto the next atom, and they just kind of domino effect right through all of the atoms and pop out the other side, and boom, you've got power to your light bulb. Yay! Also, because these atoms have a delocalized group of electrons, they're not as tightly bound as we might think, and they can shift around a little bit, and they can conduct heat through kind of like atomic friction, if you will. Your book talks about band theory, which is way above anything we need to know right now, and it goes right back into the molecular orbital models that we kind of jumped right over last chapter. We do need to discuss alloys for a little bit. Alloys are mixtures of elements that still have metallic properties. It might not all be metals, but usually the primary element, 60, 70, 80, 90% of the alloy is a metal, so it still has largely metallic properties. There are two types of alloys, the substitutional versus the interstitial. Substitutional alloy, one element has been removed and in its place, or substituted, if you will, a similar element. And the picture on the right there, you see the substitutional element. Most of those atoms, the gray ones, are iron, and the yellow ones that have been smacked into there in their place are chromium. So the chromium provides some extra properties to that alloy. More common is steel. Steel often has carbon atoms put into there, but carbon is drastically smaller than iron, and so it fills in the gaps, those tiny little holes between the iron atom. It fills in the tiny gaps between the iron atoms. And so it's filling in these tiny gaps, not replacing them. It's not a substitutional because it's not replacing a carbon atom. It's filling in the gap. We call that an interstitial alloy. And interstitial alloys with those non-metals stuck in those gaps typically reduce the ability of that element to conduct electricity, because what would non-metals do to the delocalized electrons? Well, they would make them a little bit less shifty, because nonmetals have higher electronegativities, so the electrons can't shift around as well from one element to the next element. I'm back. I'm back because I need to go to the board again. So network covalent bonds really just occur when we have one atom again and again and again. One atom again and again and again. But wait, didn't we just have that with that metal stuff? Couldn't you have iron, 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 iron? You could, but with iron, 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 those all have very low electronegativities, and therefore their electrons can shift around a lot. If we're talking about a non-metal, like carbon up here, my buddy carbon, it has higher electronegativity, and so it is not going to let its electrons just shift around. So it's going to be able to make a bond to the other carbon atom, and then that bond might repeat, repeat, repeat. So these four electrons are going to bond in four directions, and they're going to bond to only carbon atoms. And there's going to be more and more and more and more carbon atoms. And that's the only thing that's going to be in there. It's not going to be these tiny little CO2. No, no, no. It's going to be carbon, 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 carbon in all directions. Hundreds and thousands and millions of carbons. So huge. When we call these things special molecules, so they're not really molecules though, even though they're held together by covalent bonds. When you think of a molecule, you probably think of these tiny, discrete things you could easily draw. This doesn't end. It just keeps going left, right, top, bottom, out of the board. It's three-dimensional. And if it's just a whole bunch of carbon, there are three, why am I using my three like this? There are three common names for pure carbon. One is diamond. Diamond is just a giant lattice of carbon to carbon to carbon. Every carbon is in a tetrahedral shape. And because of that, the energy can be spread from one to the next to the next. And when you put pressure on one carbon, it goes through the bonds to the next couple of carbons. And the energy can be spread and spread and spread. The other common one, that's one I know I can afford, is the graphite. Graphite has bonds in three directions. It has to one carbon, another carbon, and then the third carbon. But notice the third carbon has a double bond. So it's sp2 hybridized because it's trigonal planar. And with graphite, that's this drawing right here. Graphite occurs in big giant sheets. You have a sheet of carbon, and then underneath that sheet of carbon, you have another sheet of carbon. And guess what's underneath that? Another sheet of carbon, another sheet. And each sheet is sp2 hybridized carbons in a big long layer. I sometimes imagine graphite to be just a giant pile of paper, and then some giant comes along and starts rubbing the paper off one at a time when they write. Now the third one there is this weird looking dude here. It is called, wait for it, a Buckminster fullerene. Buckminster fullerene. Yeah. Buckminster fullerene is named after a guy whose name was, shocker, Buckminster, and then fullerene is some sort of organic compound thing talking about how it's shaped. That Buckminster fullerene is a C60 that has 60 carbons and only carbon connected into a giant ball. You might recognize that giant ball shape. It looks like a soccer ball. Can you see them? There's the hexagon right facing you, then there's a couple of pentagons, but it's only carbons. So these three forms of carbon, also sometimes called allotropes, because it's all just carbon, allotropes, are network covalent solids or network atomic solids. It's one atom again and again and again held together by covalent bonds. How is that different from what we saw a minute ago with the iron? The iron or any other metal isn't strong enough to have covalent bonds, so it has that sea of delocalized electrons. So we have two distinct categories. We have metals forming metallic bonds with a sea of delocalized electrons. We have nonmetals forming strong network covalent bonds. Both of those are atomic solids. It's one atom again and again and again, but how they're attached to each other. All right, let's go to the next slide. Alrighty, here we go again. So here's our third category of solids. We did metals to metals, also known as metallic bonding. We did non-metal to non-metal, itself to itself, network covalent solids. Now it's time to do molecular solids. Now, remember, a molecule is a non-metal connected to a non-metal, boom, boom, right? And then after they are bonded, you might have a dipole-dipole, or we might have hydrogen bonding, or what's the weakest one? Yes, good job, Nick, good job. That's right, London dispersion forces. Oh wait, no, that was Austin. Okay, all right, sorry, I get you too confused. So the molecular solids are going to be made of molecules, not one atom over and over again, but a combination of atoms. So first things first, you have to go, is that a molecule? So is water a molecule? Is carbon dioxide a molecule? Yes, they're nonmetals bonded to nonmetals through covalent bonding. All right? Now, when you cool them off enough, they might form a solid. The way they form solids is through intermolecular bonding. What type of intermolecular bonding do these two molecules have? I'll pause while you think. That's right. If you said hydrogen bonding for water, good job. If you said London dispersion forces for carbon dioxide, good job. It doesn't hurt to draw the molecules. I'm not going to draw water. You probably could do that one on your own. But carbon dioxide, very much nonpolar. But these electrons can be distributed improperly, and then it could have that instantaneous London dispersion dipole thing we talked about earlier. And that's not going to be very strong though, so you're going to have to cool it off, and when you cool it off, it could then form a solid. Dry ice appears to be white as a solid, but most people get confused when they see dry ice. They think that the dry ice is going from solid to this cloud, but the cloud you see around dry ice is not dry ice. The cloud is actually water vapor. Water gets too close to the dry ice and starts to vaporize, turn into a vapor or a cloud around it just because it's getting cool, and hydrogen bonding is starting to occur with the water molecules. So this is going to be a type of solid. You need to be able to look at the component. We'll practice this in just a second, but the key here is it's a molecule. It is between molecules, and what type of bonding is it? Is it London dispersion? Is it intermolecular? What type of intermolecular force is it? Ionic solids. Here's our fourth category of solids we're going to deal with. Ionic solids deal with ionic compounds. Great. What type of elements are in ionic compounds? Yeah, Nadia? Yep. Okay. If you didn't hear her, Nadia said that ionic compounds have a metal cation and a non-metal anion, or, because it's Nadia, she said it might even have a polyatomic ion. Good job, Nadia. Super proud of you. So this is not obviously an ionic compound. Let's erase that. Here we go. Ca, that's supposed to be an A, Cl2. You get calcium plus 2 oxidation state. Chlorine is a 1 minus oxidation state. The positive ion or cation would be attracted to the negative ion. And then they would have this repeated pattern of positive, negative, positive, negative. That repeated pattern, the tiniest version of that pattern would be called a unit cell. The tiniest version of the repeated pattern is called a unit cell, and then the giant larger version would be the lattice. Okay, here's a question. What type of solid would we have formed if it was just iron? It would be an atomic solid, but what type of atomic solid? If it was just iron, it would be a metallic atomic solid, metallic bonding. All right, B, C2H6. Is C2H6 one atom? No. So you shouldn't say metal atomic solid, nor should you say covalent network. It is not just one atom, it's two atoms. Are those two atoms a metal and a nonmetal, or two nonmetals? Good job. There are two nonmetals, so that's a molecule. The molecule is called ethane. What type of bonding would this molecular solid have? Draw the Lewis dot structure, C2H6. Let's go back to the board, which is starting to look a little gray. Sorry. C, H, 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 H. There's H's in all 6 directions. All right, I'm going to say something wrong on purpose for a second. There's hydrogens on here. It must be hydrogen bonding. Why is that wrong? Why? Even though there's hydrogens on here, is this not hydrogen bonding? Yeah? Okay, Mike's got the answer. Mike just said, I don't know if you could hear Mike, I could yesterday. Mike just said that while this is hydrogen, hydrogen has to be connected to fluorine, oxygen, or nitrogen. And usually carbon is not one of those three. So it's not hydrogen bonding. Secondly, Mike also wanted to point out this sucker's non-polar. Good job, Mike. This sucker's non-polar. All the hydrogens are balanced out, so it's not even a dipole-dipole. It would only have London dispersion forces. All right, let's go to C. C was actually the example I accidentally had up there a second ago. It would be ionic, so it's an ionic solid. Graphite is a common enough compound out there in the world that you should know it's made of just pure carbon. You need to know that carbon has three common allotropes. It has graphite, diamond, and what's the other one? Buckminster fullerenes, yeah. People also sometimes talk about carbon nanotubes and carbon fibers and things like that, which are also just carbon, 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 carbon. All right, let's look at E. What is E? E is a molecule of fluorine to fluorine. It would be one fluorine to another fluorine, so it is a molecule. They are bond covalently together, so it's going to have to be in that covalent situation. It's not a network covalent solid, though, because the fluorine is actually bonded to the fluorine, and that's it. You can't draw. Let me erase this. Let's make this real clear, because some people messed up on the last test. Fluorine has how many valence electrons? Yeah, that's right, Zog. 7. Right? It's got 7. How many bonds can fluorine make since it's a second energy level atom? It can only make 1 bond. So the other fluorine bonds to it, and they're sharing these electrons in common, and now it's 1 molecule, and that's it. You can't bond another one to it through covalent bonding because it's already bonded, and that's it. They're both at 8, so that's the entire molecule. So that answers that question. We have a molecule of fluorine. So then the second question is, what type of molecular solid would it be? If it's a molecular solid, it could either have London dispersion forces, dipole-dipole, or hydrogen bonding. Whoa, 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 whoa. It's got to have hydrogen bonding. That's fluorine. Okay, you got like half of it. It's got fluorine. What is it missing that it can't be hydrogen bonding? Yes? Good job. There's no hydrogen. That's a pretty key component to all hydrogen bonding. So if it doesn't have hydrogen, it can't be hydrogen bonding. Also, it's non-polar. It's pretty balanced. What else could we say? Well, it's non-polar, so it can only have London dispersion forces. All right, let's move on. So I found this summary page of the 4 common solids that we deal with. We deal with metallic solids, which are 1 atom held to another atom, C of delocalized electrons. We have the ionic solid, which is a network of ions held together by positive, negative cation, anion interactions. We have the covalent network solids, which are the same 1 atom bonded to each other a billion times. We saw carbon examples. There's also silicon examples out there. And then we saw molecular solids, which are molecules with the 3 types of intermolecular bonding. All right, so we're going to stop there for right now. There's still some more to go in the notes, but we're not going to go any further. This gets us as far as we were supposed to get. You have time in class to do worksheets A and B. That's A as in apple, B as in bismuth, or boron, I guess would be a better choice. So A and B, that's your homework. And maybe start looking at some of those quizzes also. Okay, talk to you guys later. Have a good day.